Yes, I'm Peter Chen, the section chairman of the keynote session. It is our great honor to have Professor Mike Stonebraker of MIT to be the keynote speaker of this opening session. He's a pioneer, entrepreneur, and world-famous professor in computer technology. He got a PhD from Michigan in 1971, and then he became a professor at Berkeley from 1971 to 2000. Then he joined the MIT faculty from 2001 to now, and he's received many awards. Certainly, we all know he got the top award in computing. That's the ACM 2014 Turing Award. Now, I'd like to stress several points. Even some of you know him or know his name for a long time. He's a pioneer in computer technology, particularly database technology. As we all know, we are using databases in our daily life. Without a database, we are in big trouble. Making an airline reservation, getting money from the bank, we probably cannot do it easily. Now, in the 1970s, Dr. Ted Cott proposed a relational data model. At that time, people don't know whether it's working or not. Professor Stonebraker is one of such pioneers. He started an Ingress project at Berkeley to demonstrate the feasibility of the project. Later on, he made it a commercial product, started a company, and the company was successful and then acquired by another company. Then he developed the next version, post-Ingress, adding the abstract data type and other features. That one was also very successful and acquired by Informix. And Professor Stonebraker became the CTO of that company for a while. The other thing I'd like to mention is he's helping a lot of students. So he has probably more than 30 PhD students, and many of them get into a very distinguished career, either as a distinguished professor in major universities or forming different companies, become CEO, CTO, and many important issues. So if you look at the list of his students, basically look like a who's who in database technology. That's really very rare in any fields. I cannot see such a long list of distinguished students. The other thing I'd like to share with you is there are two special things I really admire of Mike. First, he's very persistent. He knows his goal clearly. So he just started working on and keep on and trying. As we know, in our daily life, we always have run into many difficulties, obstacles. So some people just give up, but he's not. He keep on trying. So this can be seen by his forming of different companies. Each company has different problems, and he always trying and make successful. Similar in his career, he doing the same thing. So try different things and try different ideas, and then he also make another things famous in his daily life. As we probably know, at least when I was a student in graduate school, I was dreaming to drive a car across the United States, from West Coast to East Coast, from East Coast to West Coast. Just want to do it once, but I have never done that yet. That dream probably won't happen. And then, as many of you probably have the similar dreams, Professor Mike Stonebraker actually make a very innovative type of thing. He and his wife work riding a bicycle, not driving a car, across the United States for 20 or 30 days. So certainly, as you know, by riding a bicycle, you have to climb up mountains and going down, and so just like our daily life, we have up and down, and run into different kind of problems. Then we solve the problem, we will be very, very happy, and then maybe next day or next week we will have another problem coming up. So the key thing is keep on trying. So never give up. Set your goal and keep your best, try and make it happen. So this is one of the special characteristics of Mike I admire most. There's another one I admire, which is non-stop innovation. What does that mean? Many people, when they reach a certain stage of life, maybe they make enough money, or maybe they achieve certain status in their profession, or maybe they get some prestige award. Then they say, "Oh, this may be enough. I just enjoy other things." Okay, so Mike never think about that way. He could have, after receiving all kinds of this prestige award, certainly the Turing Award in 2014. So that's about 8 years ago. So that's, he could have go fishing or play golf, but he still keep on innovation, keep on developing new ideas, keep on developing new companies. So I think in my last count, he probably developed or started maybe many projects, and including probably 10 companies. So that's a rare type of situation. So we like to learn from him. And at least myself, I like to treat that as one of my role models. Now, so today we are really very honored and excited to hear one of such new ideas, because he has so many great ideas. So what is his great idea now? One of the great ideas is the DBOS. That's the topic of his talk today. Basically, is he talk about database technology could be used to develop new type of operating system, because the operating system architecture was developed in the last 40 years was too old, too outdated. We should be able to use new advanced database technology to help to design a new system. So let's go. So this is the talk we are expecting for the whole Congress. So let us welcome the DB superstar and Turing Award winner, Professor Michael Stonebraker.
Thank you, Peter. I just wanted to make a couple comments. It pains me to realize, Peter, that you and I are both old. The reason I know that is that we've known each other for 49 years as professionals in the field. Second thing is, it actually took my wife and I 9 weeks to ride across the United States. The only reason she was willing to go is we were welded together on a tandem bicycle, and believe it or not, we're still married. So thank you very much for having me as your speaker, and good morning in the US, good afternoon in Europe, and good late evening in the Far East. So what I want to do is tell you about a new project that we have ongoing. And this is not your typical incremental, I'm going to do a little bit better on the current state of the art. This is a project to blow up the current state of the art and replace it by something completely new. So we're writing a new operating system, as Peter said, based on database technology. Who are we? We're a group of students, professors, and postdocs, and and sort of practicing professionals from MIT, Stanford, Carnegie Mellon, Lincoln Labs at Google, and VMware. So next slide. So what's the context? Well, as I said, Peter and I have gray hair. We've been around for a while. So I was one of the early users of Unix in 1973. And, you know, Unix sort of turned into Linux, and it's been around a long time, like 50 years. And so it's elderly software. The architecture is very elderly at this point, and Datacom TCP/IP is just as elderly. Next slide. So the problem is that the world has changed a lot in the last 50 years. So when I first ran Unix, it was on a uniprocessor PDP-1140 with very limited main memory, small amount of disk, and poor connectivity. As we'll see in a minute, we're doing experiments on DBOS on something called the MIT SuperCloud, which is just a bit less than 10,000 cores with terabytes of main memory, and of course the internet is ubiquitous. So the state that you've got to manage, and when I say state, that's files, tasks, messages, all that stuff, is just massively bigger than it was way back when. So think of it as 10 to the 5th bigger, 10 to the 6th bigger. So when you're managing a gigantic state without even thinking very much, that's a database problem. You know, databases are very good at managing a very large amount of data, and that's the state that has to be dealt with current system software. Next slide. So way back when, you had a single uniprocessor, a CPU. There was no notion of GPUs, no notion of TPUs, FPGAs, you know, RDMA, none of that stuff existed. So there was no thought of heterogeneous hardware way back when. And there was certainly no thought way back when of ML and AI. That basically was not the mainstream force it is today. And there was no thought of keeping track of provenance, which is how did the current state of affairs get to where it is now? So the world was just way different back then. And Unix and Linux are struggling to evolve with all of this change. Next slide. So how do I know that? Well, Linux is still struggling to add multi-core support 10 years after they started trying. And the reason is that Linux is a patchwork of modules and interfaces that just makes this challenging. Linux has no support for multi-node computing. So if you are running multiple nodes in a private or public cloud, Linux has no support for that. Ditto for provenance tracing, and security is now a really, really, really big deal. And the community is proposing new security models, which you know, have not been incorporated into Linux yet. Next slide. So just for example, if you were running Linux on a multi-node computer, whatever your favorite computer is, it's very, very likely to be a multi-node system. Then you can run Linux on each node of that system. But if you need to worry about multi-node resources, meaning you are trying to write an application and the application serves a variety of interactions, and for load balancing and scalability purposes, you want to run that application on multiple nodes. Well, Linux has no support for you. And multi-node resource managers, things like Kubernetes, you've got to run something which is entirely different than Linux, entirely different way to bring it up, configure it, and so forth. And if you just think about this for about a millisecond, you would rather have a single resource manager managing all your resources than a potpourri of independent systems doing it instead. Next slide. And then, of course, finally, why is Linux slow to evolve? Well, it's an elderly software system. Most of the code is long in the tooth and often kind of pokey. And of course, new capabilities are very slow in coming and difficult to add. So the netnet, with the next slide, is, in my opinion, it's time to throw away the Linux stack completely and rethink operating systems from the bare metal on up. So that's what our project has done, is doing, and will continue to do. So what does our stack look like? It looks nothing like the Unix Linux stack, other than you can run user programs, just like you can run user programs now on top of Linux and or Kubernetes and or ... So user programs run at our what we call level 4. They are protected from each other and from the rest of the operating system, which runs at levels 1, 2, and 3. So then at level 3, most of Linux is what I call support routines. There's, ls to list the contents of the directory, change dir to change your current directory to someplace else, change mode, change the protection status on a file. You can read and write Linux files, and the list of system calls for support services goes on for a while. So those, of course, run at level 3, and they're very different in our stack because they are essentially all written in SQL. So SQL, for those of you who don't know, who've been under some rock for a while, is intergalactic way to talk to database systems. So support routines are written in SQL. They're basically SQL applications, if you want to think of them that way. And they run on top of level 2. And level 2 is a database system. So a lot has happened to database technology in the last 30 years or so. So most of the serious DBMSs run multi-core, multi-node. So distributed database services across the nodes in a cloud is something many database systems do now. Online transaction processing is a very important subset of what database systems do. There has come to be a specialized collection of OLTP DBMSs that run at very high performance. So don't think MySQL, don't think Oracle, don't think Postgres. Think main memory, multi-node database systems with specialized concurrency control, specialized recovery, and a high performance way of dealing with multi-threading. So right now we are running VoltDB, which is one of what are called new SQL DBMSs. It is very high performance and, in our opinion, fast enough to be in the kernel of an operating system which has to do stuff at very high speed. So, of course, The DBMS requires a microkernel underneath it, and we have in mind the minimalist of microkernels. You need raw device support. You need to be able to move bytes between nodes. You need interrupt handlers, but not much else. So next slide. So pictorially, what our stack is talking about is there's a microkernel running on each node in a multi-node DBMS. The distributed database runs on top of the microkernel at each node, and it provides SQL services across the multiple nodes in this computing system and at very, very high performance. So it supports SQL across the nodes of a computer network. And so on top of SQL, we have written the file system, so you can read and write, change dir, open, close, that stuff. One of the things an operating system has to do is schedule tasks. So we've written a scheduler. It's written in SQL. You've got to be able to send messages, so-called interprocess communication, IPC, and to no one's surprise, that is implemented in SQL. And any other OS services that you need, think SQL. So that's level 3. And on top of that are typical user applications. If you like Spark, Spark lives up there. If you like Lambda as a computing platform, Lambda-like things live up there. So that's the architecture we are building. Next slide. So if you have to summarize our point of view, well, Unix was, in our opinion, revolutionary in the 70s. And they had a mantra, which is everything is a file. And that dramatically simplified writing an operating system. And Ken Thompson and Dennis Ritchie, in my opinion, were geniuses way back then. But the new mantra is everything is a table. We don't see any advantage to having a more complex data model. Relational tables, everything goes into a database system. So think all operating system state, regardless of what it is in the database system. And the DBMS is fast enough to allow you to read and write that state as necessary and keep up with adequate performance. Next slide. Or put differently, if you look at Linux and Unix, everything is a patchwork of C and C++ that's been extended and modified and maintained for 50 years. And it's getting hard to change it and extend it and add new features. The new mantra that we are trying to proselytize, write system services in SQL. When SQL by itself is not adequate, well, then stored procedures. So some SQL systems do not have, for example, transitive closure. So if you need transitive closure, well, you need some iteration around SQL. You can write that in the stored procedure language that VoltDB and many other systems support. If all services are written in SQL and stored procedures, that makes them easy to change, easy to extend. So the whole idea is that this is a much more robust environment off into the future. Next slide. So if I had to summarize, analytics, a lot of operating system services are analytics. When you type ls, you're asking for a list of all the files in your current directory. So that's an analytic query that simply reads operating system state. So if operating system state is in the database, then analytics are in SQL. and you can do wildly better analytics because SQL is a very powerful language for accessing data, and SQL is much easier to write than C++. So any analytics you want to write are easier and better. And a lot of operating system stuff is about monitoring what's happening. Well, if it's all in the database system, then you just run queries. So monitoring is a lot easier and can be made a lot more robust. And fundamentally, DBOS is a multi-node, multi-core operating system. No need for Kubernetes or a separate cluster manager. And by the way, VoltDB gives you transactions for everything. So you get transactions for all operating system state. And the OS community has figured out that transactions are actually a really good idea. And when you create a file, you'd like that to be transactional rather than maybe it will disappear if it crashes really quickly. And when we try this whole idea out on operating system folks, as you can imagine, they are terrified. Well, that's not the way they put it. They say you can't possibly make this stuff be fast enough with your architecture to compete. And I've heard that observation before. Relational database systems way back when, in the 70s and 80s, that was the standard lingo. You can't possibly make this newfangled stuff fast enough to be interesting. So of course, what we are doing is building this and demonstrating that, in fact, it is fast enough. Next slide. So here's the DBOS plan. We have implemented a thing called DBOS straw. Think of this as the three little pigs. So the first house we're building is a straw house, and it's a bunch of performance experiments in user code to demonstrate that we can do a file system, a scheduler, and IPC competitively with current system software. And most of our experiments are running on the MIT SuperCloud, which is 9,000 or so cores. And we've recently migrated to the Google Cloud Platform, GCP. And that piece of DBOS is now done. We've moved on to DBOS Wood, which is a stronger house. Second little pig lives in DBOS Wood. DBOS Wood is an end-to-end system so that you can code anything you want to in DBOS Wood, but it's still running in user code on top of current system software. DBOS Wood is well along. I'll tell you a little bit about how fast it is and the way we're doing it. And so we are about to embark on DBOS Brick, which is DBOS Wood running on top of the bare metal as a full operating system. So we've done straw. We've mostly done wood, although we're not quite done. And we're going to be moving on to brick. Next slide. So as I said, we're building right now on top of VoltDB. VoltDB is a main memory database system. It is fundamentally a multi-node system. So all tables in VoltDB are partitioned across the nodes. So think all the A's are on node 1, all the B's are on node 2, and so forth. You can partition tables any way you like. Tables are fundamentally transactional. So ACID guarantees, in fact, serializability is guaranteed for all tables. One of the nice things about OLTP DBMSs is customers who want OLTP DBMSs want them to stay up 7 times 24 times 365. So high availability is a must-have in the OLTP world. VoltDB supports HA. Tables are replicated sort of partition by partition at different nodes. If a node fails, you automatically switch over to a backup and keep going transactionally. So VoltDB masks all node failures, many communication failures, and all storage failures. And VoltDB is very, very fast in ways that I can describe if people are interested. But the VoltDB guys have run experiments on, say, an 8-node cluster, and they're happy to do 3 or 4 or 5 million transactions per second. So they can do millions of OLTP style TPSs on a very vanilla cluster these days. So it's very fast, it's main memory, and it's SQL, and it stays up, and it's transactional. Next slide. So for DBOS Straw, we wrote a scheduler, we wrote a file system, and we wrote an interprocess message system. So all of these are VoltDB applications on top of this multi-node database system. Next slide. Next, thank you. So if you're going to do operating system state in the database, then you have to do what's called a schema design. So you need to decide what tables you're going to store and what's going to go in those tables. So if you're writing a scheduler, every time there's a task that you'd like to have scheduled, that's a row in a task table, which is, of course, partitioned across all nodes. And you need to have what's called a worker table, which is how many resources you have at each node, basically the available capacity to execute stuff. So what does scheduler have to do? So to schedule a task, you have to assign a worker with available capacity to some, you assign a worker to some task in the task table, and you then move the task from queued to assigned. You decrement the capacity of the worker table by 1 for the worker that you've chosen. So think of this as a bunch of little bitty SQL on top of 2 tables. Next slide. So we wrote 3 different schedulers. They're all 10 lines of SQL or less. So if you don't like our scheduler, in 10 lines of SQL, you can write another one. And the latency of our scheduler is comparable to existing multi-node schedulers. So it is as fast as current systems. And so in our opinion, it's fast enough since it's of equivalent performance to the current competition. And of course, if you don't like ours, you can hot swap it for something else. So if you don't like ours, just write your own scheduler. It's very easy to do. Stick yours in, take ours out. So there's a VLDB paper that will be in PLVD soon. The details on exactly how this works and exactly how fast it is and who we're comparing against. The details are in our VLDB paper. If you want a copy of it in advance, just send me mail. I'll be happy to give you one. So we can do a scheduler at competitive performance. Next slide. So interprocess communication. So what does that look like in database talk? Well, you need a message table. The message has a sender. It has a receiver. It has the body, the payload of the message, a bunch of other metadata. So think of that as every message is a row in the message table. Like everything else, the message table is partitioned. So we are partitioning this table on the receiver ID. So the sender does a SQL insert of this row, which goes to the receiver's site. And the receiver does SQL query to get the payload of the message. So it's very easy to get exactly once semantics, because if a crash happens, VoltDB masks that transactionally. Can't get lost messages. VoltDB is an HA system. And so this has all the nice guarantees. And so all the receiver has to do is delete the message or leave it in the message table if he wants to keep it around. So that's how IPC works. It's simply a sender does a SQL insert, receiver does a SQL query. It's a single distributed partition table. Next slide. So how fast is this? Well, the most popular messaging system is gRPC. Our system runs at roughly the same speed as gRPC. Depends on exactly what you're doing, sometimes faster, sometimes slower, but it's ballpark with the current most popular messaging system around. Now you might say, well, what about TCP/IP? We lose to TCP/IP by a bunch, like a factor of 2. But the problem is, of course, we do an insert into a SQL table. We have to use the VoltDB messaging system to move that insert from the sender node to the receiver node. That message system goes through TCP/IP. So right now we are strictly on top of TCP/IP. There's no possibility we can do anything but run slower. So that's the first problem. The second problem is VoltDB does not have triggers. What you'd like to do is when the message arrives at the receiver site, you'd like to wake up the receiver saying, hey, I got a message for you. Instead, the receiver has to poll for incoming messages, and that's, of course, slower. So there are a bunch of ways we could speed this up a bunch. And in a bare metal system, we can do some of that. And if we had the source code to the database system, which we do not, but maybe we can get it, I don't know, we could fast path the implementation. So my sense is it's comparable to popular messaging systems, loses to the high performance ones, but there are a bunch of ways we could fix it, and we hope to in the future. Next slide. So it's probably possible to make this competitive. And the big advantage that we have is that if you don't like the way the message system works, it's easy to change. And new capabilities are extremely easy to add. So if you want to have multicast, all you have to do is add more than one row to the message table with the same payload. And so it's trivial to turn a unicast system into a multicast system, something that current IPC systems are just not easy to change. So the details of IPC, again, see the VLDB paper. Next slide. Well, what about the file system? Well, by now you get the drill. You have to do a database design. So you need to support blocks and users and directories. And that's pretty straightforward. We've written 2 implementations of file systems. The first one mimics the Linux file system, which is your home directory is on one node somewhere. and all blocks in your files are co-located at that one node. So you get a localized file system that puts all your files on the same node somewhere. So I'll call that the localized file system. The second file system we've written spreads blocks across all nodes, basically partition the file table by block number. So block 1 goes on node 1, block 2 goes on node 2, ... for however many nodes you've got. So basically, this is a parallelized file system that stores your big files. So don't bother with this for small files. So it stores your data on all nodes. Next slide. So how does this work out? Well, on SuperCloud, we'll try the bottom of the slide first. So the preferred file system on SuperCloud is Lustre. Lustre is a very similar to the multi-partitioned parallel file system that I just described, which is Lustre spreads your blocks across all nodes on SuperCloud. And against Lustre, our parallel file system basically washes. It runs at the same speed for a bunch of technical reasons that I'd be happy to talk about if you're interested. Against Linux, which is basically localized, think small files, we lose by around a factor of 2 if you're reading 1 byte. So a typical benchmark is open a file, read 1 byte. On the other hand, if you're reading a megabyte, then you're doing a bigger read. We wash against Unix on bigger reads, but we lose if you're reading 1 byte. If you're doing next to nothing, the overhead of getting into VoltDB is higher than the overhead of getting into current Linux. And so it's all in the invocation. So you could stream like that if we had the source code. So that seems to be something that's fixable. And of course, you get a multi-node transactional file system for free. Next slide. So of course, if you're doing metadata operations, like you might want to know who is the biggest consumer of bytes anywhere in SuperCloud. Well, that's just a SQL query, 3 lines of code, something that would take you a week to get running by coding it in C++. So metadata operations are wildly faster and wildly easier to code, and analytics are way less code and wildly faster. Next slide. So DBOS Straw has encouraged us to build the next version of the system because we view that our performance experiments are that their current architecture is competitive. So what are we doing for DBOS Wood? Well, we are well along at building a serverless environment. Think Lambda, think OpenWhisk. In our opinion, the future is in the cloud. The future of the cloud is serverless computing. So we have built almost all of a serverless environment on top of what we have so far. And to no one's surprise, of course, if you're the database guy, you want to leverage the database system. So tasks in our serverless environment are stored procedures. So what you do is you write a graph of subtasks. That's your overall application. We store this graph in the database. After all, it's operating system state. And we make all of your subtasks stored procedures. And then to execute, you just execute stored procedures as their inputs become ready to go. believe it or not, our initial experiments against Lambda and OpenWhisk is that we are substantially faster. So not only is this competitive, but even it looks like this is going to beat the current state of the art substantially. And if in fact you're doing something that involves accessing data, like reading or writing files, or doing, heaven forbid, database queries or updates, if you're the guy who has to write the shopping cart for your cloud application, anything that touches data, well, that is just wildly, wildly, wildly faster in our world, because you go into the database system to execute the stored procedure, and then it's a local, you simply, without any task switches or node changes, you simply access the data. So it's either better than the current world if you're not accessing data, or wildly better if you are. So the initial experiments are very, very encouraging. And what else we're focusing on besides getting this serverless environment up and scalable is we are building a provenance system that I'll talk to you a bit about. We're building a monitoring system, and we're going to build support for specialized hardware. Next slide. So provenance. Provenance is a very, very, very big deal. In the previous election last year, there was a lot of controversy. Has a given image been doctored? Did they put a bigger nose on a politician? Or who updated my salary? I didn't know I was getting a raise. Or who changed the text in an object and what did they do? In other words, I'd like to know the history of how any given object got to its current state. Next slide. Next slide. Okay, so thanks, Ella. That was a great recovery. Ella is the person doing these slides. So, provenance. So right now, it doesn't exist. Support for provenance doesn't exist in any operating system I'm aware of. If you're putting everything of interest in a database, DBMS records, files, messages, they're all database objects. And if we encourage everybody in our serverless environment to store their state in the database system, well, then to keep track of what happens, all you have to do is record all changes and optionally all reads to your operating system state. So as long as objects don't leave our environment, so as long as objects stay in DBOS, meaning you don't write them to the screen somewhere and go out of our world completely, we should be golden. What does that mean? Well, you just have to log everything that happens and then do database log processing. Well, database guys understand log processing. They've been doing it for 50 years. So next slide. Whoops. I'll go back one slide. Okay, so how are we doing keeping track of provenance? Well, we're running on a main memory database system. And so if you're recording everything that happens, that's a gigantic amount of state change. And we have to keep track of it for perhaps months. So that's something that a main memory database system is just not designed to do. So what do? We are spooling the log into a data warehouse-oriented multi-node column store that's very good at terabytes of data. So we're using Vertica. You could use and you could use Presto or some other warehouse-oriented multi-node column store. You could use Redshift, ... So log processing is spool the log into somebody who's really good at terabytes of data and running downstream queries. It looks like the overhead of spooling data transactionally, spooling everything you do, is about 20%. So as long as you're willing to pay a 20% performance penalty, we can keep track of everything essentially forever. And the vertical queries to run all the interesting stuff you'd like to know about the log, those all run with very competitive performance on big data. So it looks like Provenance simply spool the log data into somebody who's good at terabytes of data. Next slide. So lots and lots of people want to do monitoring. So monitoring means keep track of who did what. That's Provenance. But other monitoring is keeping track of who's allowed to do what. And for data lakes, what exactly do you have in this data lake, and a whole bunch of metadata. So basically, monitoring systems, we intend to build on the Provenance system, which is just augmented with other events as necessary, so that you can capture the metadata for a data lake into our Provenance system. And then it's just more SQL queries to do whatever you want to do. And of course, if you're monitoring, the memory consumption or shutting things down if things get overloaded, like everybody else today, when we're writing a monitoring, basically a watcher, it's a machine learning program. So we are going to have training data. We're going to train an ML watcher, and the ML watcher is going to watch the Provenance data that's augmented with other stuff you're interested in. So that's a research project. It's ongoing. We'll let you know how it goes. Next slide. Specialized hardware. Well, if you want to run, if you have an application, regardless of what environment you're running it in, and you want to code some of it in a GPU or some of it in a TPU, well, Linux has no capabilities that support subtasks that run on different kinds of hardware. How are we going to do that? Well, we're going to have a task table. Remember, that's in the database system for each kind of hardware. So in our serverless environment, you can have subtasks that turn out to run on GPUs or TPUs or wherever. And they simply are entered into different task tables. And the UDF is then capable of exercising different hardware, heterogeneous hardware. So we'll let you know how that goes as we get this running. Next slide. So that's kind of where we are right now. What are we looking for? We would love collaborators. We would love especially industrial collaborators. They're a terrific source of problems. In fact, the initial people exercising our serverless environment are our industrial collaborators. If you're interested in this area and you want to write code, we are always on the lookout for collaborators. By all means, get in touch with me. And if you have spare dollars that are burning a hole in your pocket, we'd love to. We are always looking for money to keep ourselves going. Next slide. So the summary of everything I've said so far, our objective is do everything exactly once. Transactions exactly once. Storage, everything goes into one database system. Place a single big bet on a multi-node transactional DBMS, this results in much simpler code, which is everything above the database system is in SQL, and you're optimizing one thing, which is this distributed DBMS. It looks like we can offer the same performance as current systems, and much better analytics and much easier to change. Next slide. And that's the end of my talk. And I hope I've made some people mad. If you have questions, comments, you want to fight with me, that would be great. I'd love to answer questions.
Yes, there's a question from Professor Mario Pacheco from University of Bari. He asked, most programmers use a procedural approach to write software. The SQL is a declarative based on base. Is there a possibility that the DB-based operating system is not understood or misused by many programmers?
Okay, well, first of all, I've been on along with Peter, I've been on a 50-year mission that if you have a lot of data, you want to access it in a high-level language, you're 2 orders of magnitude more productive than if you're coding in C++ against files. So the answer is learn SQL. And off into the future, the big data is going to go in database systems. I think that's you can't really contest that. And that means that you should learn SQL because that will be the preferred way to get at your data. And yes, it's a non-procedural world. This requires you to think differently about your data. All I'm doing is repeating what Ted Codd said 50 years ago, is that this is a different paradigm. And so yes, to learn SQL, but if you just want to code in our serverless environment, it's entirely procedural. You can write in Java or whatever. We will support Java. We will support C++ because those are the languages that VoltDB supports stored procedures in. And so you never need to touch SQL if you don't like it. You can continue to write procedural code against files. That's okay with me. I'd rather you learn from 50 years of database research and move to a different programming model. So I think part of this is against big data, SQL is a much better programming model than files.
Another question from Professor Heeman Jin. With what you proposal, you using will have open source so people can access the source.
Our code is entirely open source. And it would be really fabulous if there was a version of VoltDB that had competitive performance that was open source. And if so, our whole project could be open source. In the meantime, we're using VoltDB. Everything else is open source. At some point, we may have to write our own open source DBMS. That's just a lot of work. And so I think everything is open source that we can make open source. And so there is an open source version of VoltDB called HStore. We will probably bring up HStore and make sure it runs. Doesn't have all the features and doesn't have the performance of VoltDB. It's entirely possible that we will convince VoltDB to offer free academic licenses to everybody. They used to, and I think they will again. So I'm hopeful that we can get everything to be accessible. And there was another question, which is, can in level 4, do you have access directly to the SQL database? Of course. SQL is there. Please program in SQL.
And there's another question from Ian Foster, Professor Foster. So modern processors are highly heterogeneous with many different devices, accelerators, etc., most of which are not managed by the operating system, such as Linux. But by separating bits of code, devices, drivers, real-time OS, fragments, etc., does DBOS speak to that kind of problem?
Yes, I mean, that's the whole idea. So imagine just, for example, you have a serverless environment, and the first subtask runs on a CPU. The second subtask runs on a GPU. Third subtask runs on an FPGA. And right now, in your current world, you have to manage all that stuff manually. And as Professor Foster points out, that's a huge pain in the butt. Our idea is that you write those 3 subtasks as stored procedures. Well, our serverless environment turns into stored procedures. You simply write the first task normally. You write the second task as GPU code. You write the third task as FPGA code. And inside our stored procedure world, we are smart enough to call the correct hardware and pass it whatever this arcane stuff is that it understands how to execute. So when it's done, it simply passes control back to us. We return control, run the next serverless environment task. So the whole idea is to bury heterogeneous hardware underneath the stored procedure interface, so that we worry about executing it, finding it, executing it, and controlling it, and you don't have to. We'll see how that goes, but we'd love to collaborate with you if you're interested in working on this approach with us.
Another question. Which of the CAP theory probably is sacrificed in this design? Could one be feasible in this by selecting another DBMS engine?
Okay, so of course, so the CAP theorem from a long time ago was you can have any 2 of C, A, and P, pick any 2, but you can't have all 3. And every database system on the planet sacrifices one of those. And so VoltDB sacrifices C, so there are certain connectivity failures which will cause it to lose data. And no one has found a way to change the CAP theorem. So you can have other solutions. VoltDB gives you A and P. And you could run a different database system that had C and A or had C and P. If I'm not aware of such 2 database systems, but it'd certainly be possible. I say there's nothing magical about the way our use of VoltDB that you couldn't swap it out for a different high performance DBMS.
I have several questions. The first one is you are promoting the tables data structure. I remember in some of your work, like Postgres, you are trying to develop using abstract data type and other things. Is that because of, for the DBOS, you think using established DBMS procedure software is more easier for people to accept, or what other reason you think you should go for the table data structure?
Okay, so let me answer that. Can I give a 5-minute answer to that?
Sure.
Okay, so the NoSQL DBMSs. So there are maybe 100 of them, and they've been around for a decade or so. Cassandra, Mongo, those kind of guys. So they said at the beginning, NoSQL means you got to get rid of SQL. They said SQL is too slow, and it doesn't do what you need it to do. So fast forward about 5 years, and the NoSQL guys started saying NoSQL means not only SQL. And so they said, well, there's some problems where SQL is a good idea, but we support the ones where you don't want to use SQL. Fast forward another 5 years, and in my opinion, NoSQL means not yet SQL, because it turns out there are 100 or so NoSQL database systems, and you've got to have standards, cross operability to get anywhere in the commercial market. And so Mongo and Cassandra, believe it or not, are implementing higher level standards that, unless you squint, look exactly like SQL. So SQL, in my opinion, will take over. The big feature, in my opinion, that the NoSQL guys offer is they call it unstructured data, but that's not really what they mean. They mean JSON. And what they really mean is the ability to have 100 fields and only have data for 3 of them, and the other 97 don't have any data, and every record has a different 3 fields. So they mean, if you want to think of this as a 100 field table, it's a very, very sparse table, and they have efficient ways. JSON is an efficient way to store sparse data. Well, I have no problem with storing sparse data using JSON. In fact, most database systems, including Volt, support JSON now. So that was a nice feature that the NoSQL guys added, and gets copied by all the other database systems. So I think, in my opinion, the need for anything more complicated than sparse tables, at least in operating system state, I just don't see it. But I'd be happy to be convinced, and if so, we'll revisit it. But right now, I think as long as you can support SQL and you do a decent job on sparse data, that's good enough. And of course, the complexity of doing something more elaborate just goes up dramatically. You start to have nested transactions, ... So it just gets complicated.
Seems to me that what you talk about is some kind of conflict between advanced research versus commercial, application, commercial acceptance. So, but yourself is also play both roles. You are a professor, you are also an entrepreneur, and many people in our audience also, either in one camp, research camp, or try to develop commercial products, or both. Can you give advice to people in one camp or the other, or want to do both? What's your advice to them?
Sure. I guess my point of view for the last 50 years or so is that if you work on a problem and nobody cares about it, then you're doing theory. And so I've always looked for problems where somebody cares about the answer. And the somebody cares about the answer means somebody who does real world stuff. And so I think doing theory for its own sake, I personally don't have any interest in doing that. But lots and lots of people do. They're called theoreticians.
Yeah, that's
So
very good advice.
I guess my advice is, if you want to work on a problem, use some shoe leather and go out and find some person in the real world who wants to know the answer to what you're working on.
I remember you gave a talk and mentioning some people in the academic world just keep on publishing, each one just incremental type of thing. You would rather to see one paper, major thing, and the major ideas. So is that still your belief?
I think the biggest problem we have as a community is at least just talking about the database community. The size of the community has gone up by an order of magnitude or 2 orders of magnitude from what it used to be. And everybody has to publish in order to get tenure. So the amount of stuff that's being written has gone up by a couple orders of magnitude. And I don't know how anybody manages to keep up with it. You have a bunch of PhD students who read the stuff and summarize it for you. But I think there's got to be a good way to cut down on the diarrhea of papers. So my personal favorite is, you're at Carnegie Mellon, I'm at MIT. Suppose you got the top 20 or 30 universities to all agree that when someone comes up for tenure, they can only submit 5 papers. Right now, they submit like 50. So you can only submit 5. If you write more, we're not going to look at them. And if you are hired as a new assistant professor, let's say you can only submit 3 papers. So just make the diarrhea seems to be come from a lot of universities, especially in the Far East, who don't want to go to the trouble to actually read the papers, but just want to count numbers. You've got to interrupt that and stop it, because otherwise, just the amount of stuff being written is just overwhelming.
There's a question for the audience from Professor Michael from Eddie Chung. What are the main criticisms on your approach and result from the operating system community?
Well, we actually did write a paper that was oriented to the OS folks, and it said roughly what I've already said. So their main criticism was, prove to me that you can scale to 100,000 nodes in a real commercial setting. So basically, write a commercial version of this in order to get our attention. That's, of course, a daunting task, but we'll do what we can. But I think the big problem is the operating system community has been doing things one way for 50 years. And this has to be totally threatening to them, because it basically says operating systems are a data management problem primarily. And just like big data is a data management problem, the scope of what's a data management problem is becoming larger and larger. And that's just the way it is.
Thank you, Professor Mike. Let's thank Professor Mike Stonebraker for this excellent talk. And we will pass the podium to the program chair, Professor Jia Chen, and conference chair, Professor Wang Chen. Okay, let's thank Professor Stonebraker again. Thank you.